Hi everyone, here are just a few quick summative notes to Chapter 18. I just kind of want to bring it all together to make sure that you're hearing it maybe for a second or a third time, and hopefully it just sinks in. So a quick review of important vocab and symbols. We've been talking about parameters versus statistics. Your parameter is always specific to the population that we are talking about, and your statistics are specific to your samples. So when we are doing notation, if you're asked to represent or asked what is your parameter, you're either talking about mu or p. Right? Mu would be the true mean of the population that we're looking at. P would represent the true proportion of the population that we're looking at. And then because we never really can look at a full population, we use a sample to be representative of the population, and our notation that we use for statistics is X bar for mean and P hat for proportions. Okay, so whenever you're asked to identify a parameter, you should be saying like mu is equal to the true average of people with brown hair that live in the United States, or P is equal to the true proportion of I don't know, black labs out of all labs sold in the United States. I don't know, just making some stuff up, okay? And then your statistics are the actual mean or proportions that we find specific to our samples. Make sure you have that notation because it's very important to have the correct notation as you go through it. So, random sample versus random assignment. So when can we say that the change in one variable causes or directly leads to a change in the other? Well, when we assign treatments randomly, right? So if you remember back when we were doing our experiments, if we do random assignment, that's when we can do cause and effect, if we do a well-run experiment. When can we apply whatever results we get in an experiment or survey to a larger population? Well, that's when the subjects are a random sample from the population. So we need our samples to pass the random condition. So how do we pass the random condition? Well, we either are told that it was randomly created, which makes it easy. If we're not told that there was a random sample, then we must then say, assume that our sample is representative of the population. Okay, so to check off, so those statements that you're going to write for the random condition are either going to say state it random or state it simple random sample, or if it doesn't state it, then I'm going to say I'm going to assume that my sample is representative to the population, right? Because that's why we need random samples, so that we can say that our sample is representative of the whole entire population. So if it's not given specifically the word random, then we're going to have to say, well, I'm going to assume that this sample is representative of our population. If we were actually out in the real world, then we would probably be a little leery in our results if we didn't quite have a random sample. Okay, so make sure you have your random condition down. So chapter 18, we started with proportions. So again, your random variable for one population is p hat. Your parameters, your mu of p hat is equal to p, and your sigma of p hat is equal to the square root of pq all over n. Those are directly pulled off of the AP formula sheet, so those will be given to you. You don't need to have them memorized. And if certain conditions are met, we know that the sampling distribution will look roughly normal, right? The sampling distribution, not the population distribution. The sampling distribution will look roughly normal. Okay, so remember these are the conditions that we had for proportions. So these conditions make sure it's okay to 1, use the normal model, and 2, trust the probability we calculate to truly represent what we want to find. So again, we need to have a random sample. So was a random sample taken? If not, then we must say that we're going to assume the sample is representative of the population. Independence, so how do we check independence? Well, in this case, we're checking independence based off of the 10% condition. right? So if sampling has been made without replacement, then the sample size n should be less than 10% of the population size. This ensures that the probability of the event happening does not change much between trials. And then we want to check for normality, right? And to check for normality, I think Skew the Script was using the large enough condition is what they were calling it. So I think our book uses normal enough. You're going to read your book tonight for homework. The normal enough condition. So you might hear me say the word normality often. So let's check for normality. Well, in proportions, how do we do that? Well, we make sure that we have at least 10 successes and failures, right? So if I have at least 10 successes and failures, then my sampling distribution is going to be roughly normal. So with all of these conditions met, we then can use the normal model to represent the sampling distribution of proportions, right? Okay, so I'm going to go and work through a problem here and just kind of do the whole setup. So we have a polling organization asks a simple random sample of 50 first-year college students how far away from their home, or how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. I can't talk this morning. Find the probability that in the random sample of 50 students, more than half of them go to college within 50 miles of home. So what we're going to be doing is setting up our full worked out solution. So for a full worked out solution, the first thing you always want to do is identify what your parameter is. In this case, we're talking about proportions. So my parameter is P, so the proportion representative of the population. So my P in this case is the true proportion of first year college students who live within 50 miles. I guess I could have said that. Who attend college within 50 miles from home. We'll say. I think I got it. We got the idea. Okay, so always start with finding your parameter. Then we want to check our conditions to make sure that we can use the normal model. So what are my conditions? Well, our first one is your random sample. So are we given that it was a random sample? Yes, it is. So I'm going to write that it was stated in SRS, or just state at random would be fine. Independence, we do the 10% condition. So I would say that 50 students is less than or equal to, I guess it is less than 10% of all college students, all first year college students. Okay, so the random condition, that tells us that our sample itself can be generalized to the whole entire population. Independence lets us know that one probability should not affect another one, right? And then the last one is our normality condition, which in this case is success failure. I'm going to write out normality just because it's less writing. If you want to write out success failure, you can write out success failure. That's up to you. If you want to write out large enough, you can write out large enough. What really matters is the blanketed statement saying why it is normal. So in this case, we need to check our NP. So my N is 50. My P is 35. So 50 times 0.35, I don't know why I'm getting my calculator out, is 17.5. That's greater than or equal to 10. And NQ is 50 times 1 minus 0.35, which would be 50 minus 17.5, so 32.5, which is greater than or equal to 10. Okay, so I stated my P, my parameter. I've checked my conditions. I'm going to erase this. So then what I'm going to say is that I'm going to say with conditions met, I can use the normal model to represent the sampling distribution. Oops, I only put up in there. Sampling distribution of proportions. Okay. So what normal model can we use? Well, let's write it out. So my normal model is different depending on what your mean and your standard deviations are, right? So let's go ahead and find our mu. Our mean of p hat is equal to p, which is 0.35. So there's our mean. And then our standard deviation of p hat is equal to the square root of pq over n. So what does that get us? 0.35 times 0.65 divided by 50. And square root it. Gets me about 0.067-ish. So 0.067. Okay. So I got my conditions checked. So now I'm claiming what model I'm going to use, which in this case I'm using the normal model. Make sure you specify what your mean and your standard deviation is. Show your work for the formula of your mean and your standard deviation. And then I always like to make a picture. So here's my picture, 0.35, right? And so what are we going to try to do? So find the probability that in the random sample of 50, more than half of them go to college. So that means that my p hat is going to be 0.5. 0.5 is to the right of 0.35. So let's call it right there. All right, so now we're going to find a z-score. So our z-score, we do p hat minus p all over our standard deviation of p hat. So 0.5 minus 0.35 divided by our standard deviation, which was 0.067. Alright, so what does that get me? 2.2388 for my z-score. Okay, so now more notation. So what are we looking for now? So we're finding the probability that my p hat exceeds 0.5, right? That's what we're looking for, which when we standardize that, it really is finding the probability that my z-score exceeds 2.2388. Okay, and now it's just a matter of calculator work. I should have my calculator on here. So how do we do that on our calculator? Well, we go to second and then vars. Get rid of that. We don't need to see that. Give it a second, just in case you forgot. So we go second vars, normal CDF. My lower is, in this case, because we're doing a right tail, my lower is my z-score of 2.2388. My highest is 999. We standardize it, so that makes my mean 0 and my standard deviation 1. I'm going to hit enter, and then there is our probability. So 0, 1, 2, 6. So let's bring this back. So my probability is equal to 0.0126, I think is what I said. Okay, so I checked my conditions. I made a statement saying my conditions have been met, so I can use the normal model. I showed what specific normal model I'm using with the specific mean and standard deviation. I showed the work and where those came from, right? And then I made a picture of my normal model with my shaded region. I showed my work on how to find a z-score, and then this is at least worth 2 points in my assessments when I give it to you. notation-wise, probability that my p hat is larger than 0.5, p hat that my z-score is greater than 2.2388, and then you don't need to show me what you typed into your calculator to get that 0.0126. You just write it down. So then the only other thing I need to finish up with is a conclusion in context. So, according to the normal model, always start with this, reference the model that we're using, because we'll be using other models as we go down the road. So according to the normal model, and then rewrite your statement of what you're looking for, the probability that in a random sample of 50 students, more than half, sorry for my chicken scratch, half of them go to college within 50 miles of home. Home is about, so it's not exactly, 0.0126, I think is what the number was. Okay. Oh, given the true proportion is 35%. Is 0.35. Okay, so given that it's true that my proportion is at 35% of all first years, then the probability that in a random sample of 50 students, more than half of them go to college is about 1.3%, which is pretty darn small, right, for that to happen. Okay, so that is a full write-up of proportions. So you want to make sure you do all of those things. So I think I have it summed up here, right here. So basic steps for solving probability. Make sure you define the parameter in words. So P is the true proportion of whatever. Check your necessary conditions and write them out. Don't just think about them. You have to physically write out statements for each of them. Find the mean and standard deviation of P hat using formulas. Use the normal model to find the probability. So find your z-score and then use the z-table, or in our case, we're just using our calculator. And then always interpret the probability in context. So write a sentence explaining what the probability that you found means, right? What does it mean? Which is what we did. Okay, so now we're going to jump over to, I think this is over to our means, right? So sampling distribution of means is what you should have listened to notes on 6.4 from Skew the Script. So we're going to work through one of these problems together. So adult female heights in the United States are roughly normally distributed with a mean height of 64 inches and a standard deviation of 3 inches. What would be the probability that one randomly selected female is taller than 64 inches? Well, that would be easy. So if my mean on my normal model is at 64, right, and we're told our mean is 64 and our standard deviation is 3, and we want to go taller than 67. So I would just find my z-score of 67 minus 64 and divide it by 3, which is 1. I don't know why I was about to get my calculator out for that. So the probability that my sample, or my person, x bar, I guess, is greater than 67, I guess technically it's not x bar, it would just be x because it's just my one person, right? Is 67 is equal to the probability that z is greater than 1, and then I would do a normal CDF on my calculator with my z-score, my left tail at 1, my right tail at 999999999, 0 and 1, which gets us about 0.15866. So if I had to write it out, according to the normal model, the probability that one randomly selected female is taller than 67 inches is about 15.9%, given that the mean height is about 64 inches of females. Okay, but that's just one specific person, right? So what if we did a lot of samples? And I think the Skew the Script went through this demonstration just explaining the central limit theorem, so I want to just kind of go through it again. So here in our diagram, we have a roughly normal, it's pretty normal, right? Very symmetric population. So if this was my population, and I drew a sample of 5, and I would get a mean of those 5, that would drop down. And I could do that again and get a new sample of 5, calculate the mean, get a new one. Get a new sample of 5, calculate the mean, drop it down, right? So if I do 10,000, notice how my parent population was roughly normal, which would make sense that my sampling distribution of all the means would also be roughly normal. Okay, where it gets interesting is when we skew it, right? So if I were to skew the parent population, if I just took a sample of 5, right, and just kept doing that, find the means, drop it down, find the means, drop it down, it's still going to stay slightly skewed, but the more that I make that sample larger, so let's do 10,000. So there it's like a little, has some skewness to the right, right? But if I made my sample size, let's say, larger, so 25, and I animate it, I think you guys get the point. It's going to drop it down a big one here. All right, so there's our 25, and then we found the mean. So if I do it for 10,000 samples, right, and then calculate the means of those 10,000 samples and drop it down, look how that looks a lot more normal at 25 as opposed to when I was at 5, right? Or if I even made it 2. If I had just sample sizes of 2, look how that looks pretty skewed, right? Sample size of 5, still slightly skewed. As my sample size gets larger, we get a bit more, normal, right? So that's where the central limit theorem comes from. I didn't mean to do that. Your central limit theorem comes from if your sample size is large enough, then it doesn't matter what your parent population's shape is, the sampling distribution of the means will turn out to be roughly normal. So the magic number is 30. There's a whole article about why that magic number is 30 and not 25. So we're just going to go with it. So we're saying that the magic number is 30. So if your sample size is 30 or more, then the central limit theorem comes into play to prove your normality condition. Okay, so let's go ahead and work through this. So central limit theorem says when the sample size is large enough, the distribution of your sample means is roughly normal, even when the population is not. Large enough means n should be at least 30-ish, right? Everyone likes black and white, so we just say 30. So here's your sampling distribution for means. So if we're looking for the population, it's x bar. So if I find the mean of x bar, then it's mu. Your standard deviation of x bar is your standard deviation of the population divided by the square root of n. And just like last time, if certain conditions are met, we can use the normal model to approximate the sampling model. So here are the conditions, right? So why are we checking conditions? 1, so that we can use the normal model, and 2, that the probability we find represents what we want. So random sample is the same. 10% condition is the same. So again, we're checking for independence there. Random gives us representation of the whole population. So now we're checking the normality condition for means. So we find means in quantitative. That's a good way to know the difference. We do means in quantitative variables. We do proportions in categorical populations. So for normality, we're checking to see if the population distribution is roughly normal, a sampling distribution of any size will also be normal. So if we're told that the population is normal, then the sampling distribution will be normal. So we could just say, it's stated that the population is normal. Or if that doesn't happen, and we have some type of skewed population, this sample size needs to be greater than 30. And if it is, then the sampling distribution will be roughly normal. Okay, So those are your two things to be checking for normality. So I'm going to work through this last problem. So adult female heights, again, 64 inches, standard deviation of 3. So if we were to take many, many samples of 10 females, describe the distribution of sample means for these heights. So what do you think? If we took many, many samples of just 10 females, do you think it would be roughly normal? Do you think it would be skewed? I don't know. I'd say heights probably are pretty normal because your outliers at the top would probably balance out with your outliers in the bottom. So I would say that it's probably unimodal and roughly symmetric. Okay, what would be our mu? So our mu of x bar would be equal to 64. Our standard deviation of x bar would be equal to 3 divided by the square root of 10, which is 0.9487. So we would be using the normal model with a mean of 64 and standard deviation of 0.948. Okay, so that's how we could describe it. Remember the basic steps for solving this type of problem. Again, define your parameter, check your conditions, find the mean and standard deviation, use the normal model to find the probability, and then interpret. So if we go back, if we take a random sample of 10 females, what is the probability that their mean height is greater than 67 inches? So let's go ahead and work through all the parts. So in this case, my mu, not p, my mu is equal to the true mean height of females in US. Let's check our conditions. So random, does it state it? State it. 10% checks for independence. I would say 10 females is less than 10% of all females. Females in US. And then for our normality, or our large enough, our sample size is not large enough, but I would say that the population of heights, the female heights is roughly normal. I don't think it's top or bottom heavy. I would say that it's pretty rough, pretty normal in the distribution of it. Okay, so I checked. So there's 1, there's 2. So now let's go ahead and find my means and my standard deviations. So with conditions met, we can use the normal model to represent the sampling distribution of means. This is really bad handwriting, I'm sorry guys. Of means. And let's see, we got mu, we said mu of x bar was equal to our mu, which is 64. Our standard deviation of x bar was sigma over the square root of n, so 3 over the square root of 10. I said that was 0.949, I'm going to round to. So I got the normal model of 64, standard deviation 0.949. Here is my normal model. Plop your median in the middle. We got our 67 up here, shade it up, find your z-score. So 67 minus 64 over our standard deviation, which is 0.949. So that gets me 3 divided by 0.949 is about 3.16. So then notation, we're finding the probability that our x bar is greater than 67. right? So the mean of our sample size of 10 exceeds 67, right? Which is the same as standardizing it with a z-score being greater than 3.16, which is going to be pretty small because we're more than 3 standard deviations, right? So now I'm going to do a normal CDF. Lower bound is 3.16. Upper bound is 999999999. Keep it at 0 and 1 because we standardize. So it's 0.0008. Pretty darn small, right? So then we need to write it up in context. Give myself some space here. So according to the normal model, and this template is going to be continuous for the rest of the year. Like, it's kind of like you just wish you had a stamp with some fill in the blanks, because you could, or just copy and paste. According to the normal model, the probability that the mean height of a random sample of 10 females exceeds 67 inches is about 0.0008 given a true mean of 64 inches. Done. Okay? So, it's a lot of work. But what's going to happen is you're just going to get a habit of doing all of those steps every single time. So, in order to be able to use the normal model, you have to check the conditions in order to use the normal model, right? So that's why it's required. You need to check those conditions. And then once you've checked the conditions and start using the normal model, do all your formulas and your notation, and then write it up in a full summary. Okay? All right, I think that was all I was going to do. I'm not going to do the mulch problem, so that concludes this video.